So, hello everyone, we will continue the last topic, that was transient growth kinetics. So, if you recall, in the last lecture we discussed what is transient growth when there is no steady state. At that time we call as transient growth, and then we discussed couple of unstructured batch growth model like Malthus law, which explains the exponential phase, logistics equation which takes care of exponential and the growth phase, and we discussed monod model as well. Further, we discussed the growth of filamentous organisms, particularly molds. There we have observed the mass is proportional to T cube. So, going ahead further we will discuss in today's lecture in the transient growth how there is a significant lag time, how we can minimize it, and in addition similar to the substrate and enzyme kinetic inhibition, we will also see substrate and product inhibition of microbial growth today. The transient growth, you can remember, this is also called diaxic growth. So, you can say there is a biphasic growth, one growth phase is here, other growth phase is here, this is phase 1, this is phase 2. And why we are observing this biphasic growth? When there are two different carbon sources. So, when there are two different carbon sources, so typically the microbe prefer one over other. So, the preferred one, let us say here there is a glucose and lactose. So, here glucose is the preferred first, followed by the lactose. So, initially the preferred one will be utilized, glucose is utilized here, it is exhausted, then there will be utilization of lactose in this phase. So, when we are seeing such behavior, so there is a lag time here, a lag time here. So, when we observe the lag time, we observe the lag time because inoculum takes time to adjust to the new environment. It may be the new media, it may be the new operating condition or environmental conditions. So, it takes some time to adjust with this new environment, and the time taken in this adjustment is, we are referring the lag phase or lag time. And once it is done, as we have seen here, there is a rapid growth, then the cells multiply rapidly, and you can quantify in terms of cell mass or cell number of living cells as their doubles regularly with time. So, here we write dx upon dt mu into x. If you integrate it, so you will get dx upon x is equal to mu into dt. You can integrate, so this will be ln x mu into t plus constant. Now, for constant we have to apply the condition x equals 1 naught as t equals t lag. Here we are not putting t equals 0, rather what we are putting t equals t lag. If you put t equals to t 0 means we are only focusing from here, but when I say t equals t lag, then we are focusing from here. This is the t lag. Then after putting the boundary condition, we will end up with ln x upon x naught mu t minus t lag, or one can rearrange x equals x naught e to the power mu t minus T lag. Only for the exponential phase, how was the initial expression? If you remember, it was only x equals x naught e to the power mu into t. The T lag term was not there. So, when you want to minimize this T lag, then one option is the inoculating culture should be active as much as possible, and when inoculum is in their exponential phase, at that time they should be transferred from inoculum to the main culture. Second option is what we discussed. The first one was the inoculum should be active, it should be in the exponential phase, and as we know, the culture medium differs for the inoculum and for the main culture. So, we should have the culture medium media similarity. It should be as close as possible, and as we have seen, the growth is directly proportional to the concentration. There is a typical size of the inoculum. Typically, we keep 5 to 10% volume by volume. So, 5 to 10% of the new medium volume, that should be the inoculum size. In this way, one can work on minimizing the lag phase. Now, we will see one example here. A culture of E. coli is grown in mineral salt medium with glucose and sucrose as carbon sources. The optical density of culture was monitored over time and data are as follows. So, with increase in the time, we can see there is increase in the optical density. So far it looks okay, but when I plot over here with time and optical density, then if you see here, it is increasing from up to 1.04, right. You can see there is a rapid increase, then it is increasing this, then there is a slowdown here, then there is a further increase. So, you just see one phase, we can see 0 to 6 hours, then second it is starting from 10 and 12 hours. Now, what it is saying, decode the various phases involved in the growth based on the optical density data and calculate the specific growth rate during exponential phase. Yeah, so as I discussed here, we are considering 0 to 6 utilization of one substrate, let us say glucose, then 6 to 8 is a diaxic lag phase, then again from 8 to 12 we are observing the utilization of second source, that is sucrose. Now, we have to calculate two specific growth rate. How we calculate specific growth rate? ln x upon x naught mu into t. So, you have to write mu equals ln x minus ln x naught divided by what is the difference, T2 minus T1. So, here 0 to 6, what was the OD? 0.025, at 6 hour OD was 1.04. So, this will be ln 1.04 minus ln 0.025 divided by 6, so you will get the specific growth rate of 0.62 hour inverse. Now, in the second phase, you can see this is a slow growth as compared to the first phase. You have to take 8 to 12. So, what will be the x naught? X naught will be 1.1. What will be the x? Will be 1.35. ln 1.35 minus ln 1.1 divided by 12 minus 8, and here the specific growth rate is coming 0.05. So, it says we observed the diaxic growth here, and it is utilizing two different substrates, and there is a significant difference in the specific growth rate value. We will see one more example here. It says a batch reactor is inoculated with 1 gram per liter biomass. Under these conditions, cell exhibit a lag phase of 30 minutes. So, what is given here? X naught is 1 gram per liter and T lag is 30 minutes. If specific growth rate in the log phase is mu is 0.00417 minute inverse. Calculate the time taken for the biomass to increase to 8 gram per liter. X is 8 gram per liter. So, we already know the expression, only the change will be T minus T lag. It says x equals x naught e to the power mu T minus T lag. So, what we need to find? We need to find the value of T here. So, we can rearrange it ln x upon x naught equals mu T minus T lag. So, all the parameters are known to us. We can quickly calculate the value of T. This will be 528 minutes. So, it will take 528 minutes, and in this 528 minutes, what is the value of lag time? That is, it already including 30 minutes of lag time, plus if you subtract 30, the rest will be the time in the exponential or the growth phase. So, going ahead, we will discuss inhibition. When there is a microbial growth also similar to enzyme kinetics, there are inhibitions observed during the microbial growth as well. So, what it says, it can be by the substrate, even your product can be inhibitor, or there may be formation of some toxic compounds or byproduct or any other foreign chemical which may act as an inhibitor. So, substrate, when it works as an inhibitor at high concentration, when it is at very high concentration, it may act as an inhibitor. Now, we have already discussed the kinetics of inhibition. So, as we have seen in the enzyme kinetics, substrate inhibition of growth may be competitive or non-competitive. So, we have already discussed this competitive, non-competitive and uncompetitive. So, we will directly use those expressions here. So, if you remember non-competitive enzyme inhibition, what was the expression? In the case of non-competitive, it was V equals V max S, it was V max apparent S upon Km plus S. And what was V max apparent? Apparent was V max divided by 1 plus I upon Ki, right. Similar to this, we are going to see here mu as mu max apparent. It means mu max divided by 1 plus S upon Ki. This is the mu max apparent to S divided by Ks plus S. Now, this can be further simplified when we considered Ki is greater than Ks, then this can be simplified as mu m upon Ks plus S square upon Ki. So, this is the case of non-competitive substrate inhibition. Similarly, there can be competitive substrate inhibition as well. What happened in the competitive enzymatic inhibition, if you remember, it was V equals V max S, there is no change in the V max, rather there was a Km apparent plus S. And what is the Km apparent? Km apparent is Km 1 plus I upon Ki. So, similar to this, if I write the expression for the competitive substrate inhibition, it will be mu equals mu m Ks 1 plus S upon Ki plus S. This will be mu m S. So, what it says, the value of Ks apparent has increased, similar to the Km apparent was increased, and here the value of V max apparent was decreased. So, here the value of mu max is decreased. So, we can quickly revisit all three competitive inhibition. In case of competitive enzyme inhibition, Km was increased, V max remains unaffected. In case of uncompetitive, both Km is reduced and V max is reduced, and in case of non-competitive, V max is reduced and Km remains unaffected. So, in case of microbial, Km will be replaced by Ks and V max is replaced by mu m. So, here both Ks as well as mu m are reduced. Here mu m is unaffected and Ks is increased. Now, similar to the substrate inhibition, there is a case of product inhibition. Means when you are producing certain metabolites, the cells has a certain tolerance limit. Beyond a certain concentration, your product itself can act as an inhibitor, and similar to the substrate inhibition, the product inhibition may also be competitive or non-competitive. In addition to this, if the mechanism is not known, then this product inhibition is expressed as exponential or linear decay expressions. So, it can be competitive, non-competitive or even single exponential. So, as we have already discussed this case, in case of non-competitive, what will happen? Mu max will be reduced. How it will be reduced? Mu max divided by 1 plus P upon Kp. So, this you can write mu max apparent. So, it says mu equals mu max apparent S upon Ks plus S. For competitive inhibition, again it will be mu max S Ks apparent. Ks will be competitive increase. Ks apparent equals Ks 1 plus P upon Kp. Kp is the product inhibition constant. So, in the case of product inhibition, we have discussed non-competitive and competitive product inhibition. Yeah, one example is ethanol is produced by this sugar, it may be glucose or sucrose, and typically Saccharomyces cerevisiae yeast is used for the production. So, what we have observed ki after a certain concentration of ethanol, we observe the product inhibition, and typically this is a non-competitive product inhibition. So, apart from non-competitive, the experimental data also correlate with a simple expression model which says mu equals mu max S upon Ks plus S. In addition, one term is added, P divided by P upon Pm to the power n. What is Pm? Pm is the product concentration at which growth stops. So, this is a function of P upon Pm to the power n. N is a constant. So, as we discussed, in case of product inhibition, even inhibition can be expressed in terms of single exponential. So, that can be explained even in terms of single exponential mu as mu max S Ks plus S e to the power minus P upon Kp. What is Kp? Kp is the product inhibition constant. Now, apart from the substrate and product inhibition, inhibition can also be observed by certain byproducts or toxic compounds, and in this case again one can observe competitive, non-competitive and uncompetitive inhibition of growth in analogy to enzyme inhibition. What will happen in the case of non-competitive? Mu max is decreased. So, mu max apparent, this will be mu max divided by 1 plus I. Here the concentration you are using I, inhibitor concentration upon Ki. In the case of competitive inhibition, we are going to have Ks value will be increased. So, this is Ks apparent equals Ks 1 plus I upon Ki. And in case of uncompetitive, what happen in the case of uncompetitive? Both mu m and Ks will decrease. So, we are going to have mu as mu m apparent S divided by Ks apparent plus S. What is mu apparent? Mu m divided by 1 plus I upon Ki. What is Ks apparent? Ks apparent here is, this is decreased, not increased. Ks divided by 1 plus I upon Ki. So, in this way, if there is inhibition due to presence of toxic compound, we should be able to analyze particularly what is the concentration of inhibition and what is the rate of inhibition. Further, what happens when there is a, apart from inhibition, these inhibitors can also inactivate the cell or lead to the cell death, and when you observe there is a cell death due to inhibition, then what mu will be decreased like mu max S Ks plus S minus Kd. So, rather we say we are discussing mu net, and mu net will be initial mu minus Kd, and Kd is the death rate constant. So, in this way one should be able to incorporate the presence of toxin as an inhibitor or as an inactivator of the cells or they are actually leading to death of cells. So, we will have one example here. It says specific growth rate of inhibited growth in a chemostat is a continuous culture, that we will be discussing in the next module, is given by the following expression. It says mu as mu max S Ks upon Ks plus S plus I Ks upon Ki. Now, can you think of which type of inhibition is this? To understand this, first I need to rearrange this. I will rearrange this mu max S. In the denominator, take Ks as common. So, we will end up with 1 plus I upon Ki plus S. Now, which type of inhibition is this? This is competitive inhibition, where the Ks value has increased. Now, with inhibitor added to chemostat, determine the effluent substrate concentration at a D value of 0.2. So, in the case of CSTR, we say mu equals D, D is a dilution rate, and this value is given as 0.2, mu m is 0.5, our inverse, S naught 10 gram per liter, Ks 1 gram per liter, I is 0.05 gram per liter, Ki as 0.01 gram per liter. Now, what we have to calculate? S naught is given. What is the value of S which is going out, that we need to find out. So, we can apply this simple expression, it is already given, competitive inhibition. So, it becomes mu equals mu max S divided by Ks 1 plus I upon Ki plus S, this equals to D. So, mu max value is 0.5, I value is 0.05, Ki value is 0.01. So, this will become 5 plus 1 6, and Ks is 1. So, this will be 6. So, we can just rearrange this. So, we will end up with 6D divided by 0.5 minus D, and if you put the value of D as 0.2, you will get the answer as 10 gram, you will get the answer of 4 gram per liter. So, S naught was 10, S will be 4 gram per liter. So, this will be 1.2 and this will be 0.3, this will be 4 gram per liter. So, in this way we should be able to understand the inhibition of microbial growth as well. So, I will stop here for this lecture. Thank you.